First, we start with the partial fraction. So what that is, so let's start with the decomposition of nx dx into a partial fraction. So what we have is, we start with something like nx over dx, and then we divide the nx dx, which in this case is clearly improper, because the degree of the numerator is greater than or equal to the degree of denominator. So when we divide it out, the degree of the numerator should be, so when we do decompose it, it would be supposed to be polynomial plus n1 x over the x. In this case, the numerator is smaller than the denominator. And then after that, we start factor out. So this is one. Step one, divide if it was improper. Step two, we factor out the denominator. So we completely factor the denominator out into factor form of px plus q to the m, and an ax squared plus bx plus c about n, where ax and bx plus 2 is irreducible. And the third step is to linear factor out. So we factor out the px plus q to the power of n. So for each factor of the form px plus q to the power m, the partial fraction decomposition must include in the following sum. So for example, it should be a1 over px plus q plus, or if we have like a continued factor, be like the next one will be a2 qx plus q to the power of 2. So we can clearly see that the one on top and the one on the bottom increases the a2 qx plus px plus q to the power of 2. And if we continue, it will be a3 over 2 p plus q px plus q to the power of 3, and etc. until we get to the generalized form as am over px plus q to the power of m. And the last step is to find the quadratic factor. So for each of the factor of this, ax squared plus bx plus c to the power of n, we factor out and then the partial fraction of decomposition must include in the following sum. So step 4 is b1x plus c1. So we completely factor that out into ax squared plus bx plus c. And then if we continue to do like that, we b2x plus c squared over to ax squared plus bx plus c squared. And if we continue like that, we b3x plus c3 over ax2 plus bx plus c to the power of 3. And then therefore we got a generalized term of b and x plus cn over to ax squared plus bx plus c to the power of n. And that's the step to do partial fraction. Okay, so let's start with improper integral. In this case, we're trying to do the improper integral with infinite integral limit. So what does it mean? So that means that from when f is continuous at the interval of a to b, but b in this case is infinity, then we have, so what does it look like? So from a we're trying to find the integral of a to b, and b in this case is positive infinity, f of x dx, and we can evaluate it into the limit of b to infinity, the limit of b to infinity, as b approaches infinity. We can do the integral of a to b of fx dx. Okay, so what happens if the integral is continuous at the interval of negative infinity to b? Then what do? In this case, we can evaluate such as the integral of negative infinity to b f of x dx into the limit as a approach to negative infinity. The integral of a to b is f of x dx. So what if it's continuous? What if the integral is continuous at negative infinity to b? Then we have something like this. As the integral of negative infinity up to positive infinity with f of x dx, we can evaluate it into two different integrals of negative infinity to c fx dx and c to positive infinity f of x dx, and that's it for improper integral. So what if the integral is continuous as a to b but discontinuous at b? Then we have the integral of a to b fx dx equal to the limit of c equal to b negative c to a a to c, the integral of a to c fx dx, and then we have, this is what we have a convergence because the limit existed. So let's say we have an interval where f is continuous, the interval of a to b, then but it's have an infinite discontinuity at a. Then how does it look like? So it looks like this. The interval of a up to b fx dx equal to limit of c equal to a plus c with the integral of c to b f of x dx. And this is what we have. This is an improper integral, which is diverges. What we call diverges, the opposite of converges. So last but not least, what if we have an integral where f is continuous on a to b, but in some c in a to b, it is infinite discontinuity, so like a hole. So how does it look like? It will look like this. the integral of a to b fx dx equal to integral of ac fx dx plus integral of c to b fx dx. And this is an improper integral on the left diverges, and then but if either of the improper integral on the right diverges. So that's it for improper integral with infinite discontinuity. So what we have next is slope field. So what is the definition of slope field? Slope field is when we have a differential equation. Slope field is the directional field that shows the general shape of all solution. So what does it mean is that we have a graph like this, like that, and we have some like 1, 2, 1, 2, -1, -2, and let's say that the slope of the differential equation of this -1, 1 is like this, but 1, 1 is like this, and at 1, 1 is like this. So we can clearly see the direction changing in this such field due to the slope of the differential equation. So that's what we have a slope field.
I suppose.
So next we have, last but not least, is the Euler rule. So the Euler rule states that it's an estimation of a curve using tangent line. Every section of a tangent line. This, that, I like that. So this is a curve, and this is Euler approximation. So it's not quite it's not quite as exact, but again, it's an approximation. So as Euler approximation. Sorry.